Excellent. Yes, so thank you. So today we'll talk about modeling malaria elimination. You may have had some talks on malaria, but in case not, I'll give just a very brief introduction to malaria first, and then talk about the models we use, how we build it, and how we use them in the particular case of Zanzibar. So malaria it's a very, very old disease. It's probably been with humans for as long as humans have been humans. So it's really evolved with us. There is sort of this picture that you see here is the Ebers papyrus. This was discovered in Luxor in the 19th century, and it's a text that goes back 3,500 years describing the symptoms of malaria, and it's thought, and it's expected that there are written tests describing malaria going back over 5,000 years. So it's really been with us for a very long time. As you know, Nigeria is the country with the highest burden of malaria. It is a disease that causes symptoms that can range from relatively mild fever to severe anemia, coma, and death. And it kills hundreds of thousands of people, mostly children, every year. It's an environmental challenge. It is a cause of poverty, but it's also a consequence of poverty. So it reduces GDP growth, and places that are poor are more likely to have malaria because it is a disease that we can treat well and that we can control well if we have enough resources. And it's been a major force in history, leading to changes in wars, and it had a huge effect in World War II, where a lot of the fighting in the Pacific was over control of quinine plantations that were used for controlling malaria. And there were many battles where more people died of malaria than actual fighting. It played a role in colonialism in Africa, in preventing colonialism. It played a role also in the fall of the Roman Empire. So it's been a part of humanity for as long as we've been humans. And now to modeling. So the first ordinary differential equation for any disease was published by Ronald Ross first in 1910 and then in 1911. And here you can see the equations, which are still the same kinds of equations we use today when we talk about malaria models, or often now called the Ross-McDonald model. So Ronald Ross was the first person first of all, he demonstrated mosquitoes' role in transmission. So before him, the mosquito was not identified as the host of malaria. Ronald Ross did it for bird malaria. And this was later followed by someone else showing that mosquitoes were responsible also for human malaria. And Ronald Ross, who is more famously now is known for developing the first model for malaria. And what he was able to do with this model was to calculate a basic reproductive number, which we now know as the number of new infections you get from one infectious case. And what Ronald Ross showed with this model was that you'd not need to get rid of all mosquitoes to get rid of malaria, but you just need to get the number of mosquitoes or the density of mosquitoes below a threshold, where R naught goes below 1, to eliminate malaria. And this led to a lot of work in the early 20th century where malaria control focused on larviciding. So it was really about draining ditches or draining ponds where water collected, cutting brush and vegetation around where water would have collected. And then in breeding sites which could not be removed, it was using oil and other larvicides to kill larvae. And a lot of this work had, again, in many places worked very well, sometimes not great. And it's really this work with larval control that enabled the building of the Panama Canal, where a combination of malaria and yellow fever made it very difficult to actually build a canal in the late 19th, early 20th century. And then just around the time of World War II, so quinine was synthesized by Bayer AG in Germany, used as a substitute for chloroquine was synthesized, used as a substitute for quinine, because quinine had been known for centuries. Quinine has worked very well against malaria, but quinine also had substantial side effects. And chloroquine, as you can see from the chemical diagrams, is similar to quinine, but has a chloride over here, and this bit is different. It was initially stalled because it was considered too toxic for human use, but then it turned out that it's actually not. So it does have side effects, but it's not as dangerous as previously thought, and far less dangerous than quinine. So around the mid-20th century, we had very good treatment for malaria. We also then around the same time discovered DDT. This was done sort of close to Basel, where I'm currently now. And what they found out was that DDT was a fantastic tool for killing mosquitoes, for repelling mosquitoes, for preventing mosquitoes from entering houses. And then George MacDonald came and he took the model that Ronald Ross had developed. He tried to calibrate this model to epidemiological data. He tried to estimate how long people are infectious, how long it takes mosquitoes to become infectious. And what he showed with some relatively simple mathematics, P here is the daily survival probability of a mosquito. And this term here is the expected number of bites that a mosquito who gets infected with malaria would have after it's infectious. So it's looking this P to the 12, sorry, is the probability that a mosquito survives 12 days to become infectious after it's infected. And then it's this is the mortality rate of mosquitoes. So it's looking at how many bites you would then expect a mosquito to have. And what you can see is that as the mortality rate reduces, the number of infectious bites, expected infectious bites, decreases very, very quickly. And through this relatively simple mathematics, MacDonald showed that it's much more effective to kill adult mosquitoes than it is to kill larvae and only decrease the number of mosquitoes. So this really pushed malaria control then in the second half of the 20th century from larval control to adult mosquito control. And this coincided also very nicely with DDT having been synthesized and people then having a very good tool for controlling malaria. And then if we move a little bit into the history of malaria control, this is the number of cases in the USA. And you can see around the end of World War II, there was a huge decrease in malaria. I mean, this is when DDT and chloroquine were introduced. Malaria actually went down a bit before, largely due to changes in housing, air conditioning being more widespread, and mosquitoes not able to enter houses. But it's really DDT and chloroquine that were then able to eliminate malaria from the USA. Around that time, in the mid-1950s, the world started the Global Malaria Eradication Program. So this was a way to really eradicate malaria from the world. They called it global. However, at the time, a lot of Africa was left out of this because it was considered impossible to eradicate malaria from Africa. So even though it says global, it wasn't really global. Some of the other issues with this is that this is the world, about 10 years after the end of the Second World War, where a lot of thinking was still very militaristic. And the malaria eradication program was conducted in a very militaristic fashion, where you had ideas of essentially squads, not soldiers, but malaria fighters that would go out. They would, in this case, spray houses with DDT, and they called it the attack phase, where they would try to essentially cover as many houses and as much of the surface area as they could, and do this for 5 or 6 years, and expect that at the end of these 5 or 6 years, malaria would have been eliminated, and then they would move on somewhere else. And some of the thinking here was very smart because they realized that over time, the mosquitoes would become resistant to DDT, so continuing to spray would not work. So the idea was to really overwhelm the mosquitoes, eliminate malaria, and then stop the interventions. This worked very well in many places, but it also didn't completely eliminate malaria in many places. And here you can see examples. This is malaria cases per 1,000 people on a logarithmic scale. So at the top here, the 100 implies one essentially 1 malaria case per 10 people per year. At the bottom here, you have 1 malaria case per 100,000 people per year. And you can see in Sri Lanka how IRS brought malaria down to very, very small numbers. However, it did not go to zero, so they stopped the program and malaria cases shot up again. And you can see they went up not as high as they were in the 1940s, but still very, very high. Here you can see the parasite prevalence in Zanzibar dropping from 80% to about 5% when they halted the program, and then going back up to 60 or 70%. So in the places where malaria was not eliminated, this was called the Valley of Death, where malaria transmission went down substantially, and then when the programs were halted, came back again. And since then, through the 70s until the 2000s, there was not as much done for malaria control until we discovered sort of the use of insecticide-treated nets, had new interventions again, and from 2007 onwards, we've had a renewed push towards malaria elimination. The current push is much more cohesive, it's more consistent, and it's really about trying to get malaria down until we can completely eliminate malaria. And for elimination, one point to make is we tend to think of elimination as having no cases. However, malaria has a very particular definition of elimination. So the WHO classifies cases into 3 types. So you can have imported cases. So these are cases that were acquired outside where you live. So if you talk about, in this case, Zanzibar, these are cases that would be acquired outside Zanzibar. This could be either people that live somewhere else, get malaria and travel to Zanzibar, or Zanzibari residents who travel outside, get malaria and come back. If a mosquito bites an imported case, gets infected and infects a person in Zanzibar, so this is a locally transmitted case, but it's a first, essentially just one step removed from an imported case. These are called introduced cases. And if a mosquito bites an introduced case, gets infected and infects someone else, that would be an indigenous case. And the definition of elimination for malaria is to have 0 indigenous cases, and for at least 3 years. And after 3 years, the WHO would then certify malaria elimination, including a lot of making sure the surveillance system is strong and so on. So for countries that are eliminating, they're allowed to have imported cases, they're allowed to have introduced cases, they just cannot have any indigenous cases. So we wanted to build a model of this for Zanzibar. So Zanzibar is sort of here. Maybe before that, I'll just talk about the current elimination situation. So the countries in white, so countries that either don't have malaria or had no malaria by the year 2000. The countries in red are countries with at least 1 indigenous case. So it doesn't matter whether it's 1 indigenous case or 100 million indigenous cases. It's just they're all considered red. Countries in green are countries that have been certified by 2022. And sort of there are more updated maps which show more progress since then. And countries in yellow are countries that have had no indigenous cases for 2 years. And blue are 0 indigenous cases for over 3 years. So these are countries that are close to elimination. I think Egypt is also now certified. And here you can see a list of countries. The green countries are countries that have been certified, and blue countries are countries that have 0 indigenous cases, right, but have not yet been certified, or at least hadn't been in 2022. So again, Zanzibar are 2 islands off the coast of Tanzania. They're semi-autonomous regions that so they have their own malaria control program. And we wanted to build models of transmission here. You can see elimination in Zanzibar previously was, very, very high, and now it's gone down to about less than 5%, largely through good treatment, long-lasting insecticidal nets, and endoresidual spraying. And a lot of malaria in Zanzibar comes from outside, and genetic fingerprinting shows that there's very close relatedness between sort of cases in Zanzibar and mainland Tanzania, and you can see the areas of Tanzania that have been importing malaria into Zanzibar. And the current interventions are reactive case detection and indoor residual spraying. And reactive case detection is really targeting house. It's used to when you have areas with low prevalence. This is a way of targeting households with the highest prevalence. So if someone shows up at the health facility, the program then follows the person home and tests either people only in the household or some of the neighbors of this person to see if they have malaria. And if they have malaria, they're also then treated. And this is a way of sort of, if you have, as transmission goes down, you have more clustering of cases, and this is a way of catching these cases. So there's some novel interventions we considered. This included increasing the number of neighbors that we tested, presumptively treating all household neighbors and household members and neighbors. So instead of testing them, just giving them drugs. Increasing the treatment seeking rate, so trying to look at making sure more people with malaria showed up at the health facility, trying to treat imported cases and increasing vector control. We started with the simple compartmental model, so we just had an SIS model for transmission, but we had a metapopulation model where we had sort of transmission in each of the two islands and the mainland with movement between them. And this is a model where K is either 1, 2, or 3, representing the two islands or the mainland. And the transmission on any island is sort of, so the number of infected people on any island. Here it reduces when people are either treated through 5K, treated through a reactive case detection program, or where they clear the parasite either through passive case detection or just being the parasite dying out on its own. These are the new infection terms. So this is the susceptible population on any island. And here we're looking at all the ways that people can get infected. This includes getting infected. So a person from, say, Pemba can get infected either from people on the mainland or Unguja or Pemba in any of the three places. So that's why you have sort of two summation signs. So one is sort of summing over where the person is and where other people are on that place. So a person from Pemba on Pemba can get infected from visitors to Pemba, from the mainland or Unguja, or from residents of Pemba. They can get infected in Unguja from residents of Unguja or other visitors to Unguja. So we sum over all of these. We then divide the infected cases into either imported infections. So these are now, here we're only considering infections brought onto Zanzibar by residents of Zanzibar, or introduced. So these are infections either from imported cases or infected visitors to Zanzibar. So we're not considering infected visitors as imported cases, but only their onward transmission to residents, and then the indigenous cases. This has been published now, so there is an article here where you can see these equations in more detail. And again, so we have susceptible people that are infected by the imported people. They become introduced or indigenous, or they can become imported if they're traveling. Right? So again, if we take the example of Pemba residents, if someone from the Pemba residents travels to mainland Tanzania, no matter who infects this person, they will be considered imported residents on Pemba, right? So this is in mainland Tanzania. If they could get infected from either someone from Pemba, Unguja, or mainland, as long as they're on mainland Tanzania at the time, they will be considered an imported case when they go back to Pemba. If they travel to Unguja, it's again the same, no matter who infects them, because they're not in their homeland, in their home island, they will be considered an imported case. For Pemba residents on Pemba, if they're infected either from someone from Unguja or mainland Tanzania who is visiting Pemba, they would be considered an introduced case. So this is not imported, but introduced now. Or if they're infected by an imported resident of Pemba on Pemba, they would again be an imported case, right? So this is sort of one transmission away. And if they're infected if they're a Pemba resident on Pemba, and they're infected by either an introduced or an indigenous case on Pemba, they would be considered an indigenous case. So this is how we build a transmission matrix for Pemba residents, and then we would similarly do this for Unguja and the mainland. Right, and this is the full description of how they're infected. So for someone from Pemba, if they're infected on Unguja or mainland because they're outside, they would be an imported case. If they're infected from an Pemba resident who is an imported case, or from visitors from Unguja or mainland on Pemba, they would be introduced cases. And if they're infected by either introduced or indigenous cases on Pemba, there would be indigenous cases. Right? And sort of all these tables we can write into the equations here. So this is the equation for the imported case, where they're, for each of the islands, they're getting infected outside the island. This is for introduced cases, where they're either infected by visitors to the island or by imported cases of their home patch, on their home patch, or indigenous cases where they're either introduced or indigenous cases of residents on their same island where they get infected on that island. We then parameterize, I'm going to run out of time soon, so we parameterize this model to data from Zanzibar based on how many tests we had. We calibrated the transmission rate from prevalence data, and then we simulated the equations using a stochastic model. So this was a Townley adaptation of the Gillespie algorithm to capture stochastic illumination. And we know that even importation is low. Most of the cases are indigenous cases because people are infected with malaria for a very long time. We also then looked at the impact of all these interventions, and we saw that individually each intervention had a relatively small effect. So this is the baseline. These are each of the different interventions. You can see that they don't do very much individually, except for treating almost all travelers. So if you significantly reduce importation, you can have a big effect. But if you stack all the interventions and put them together, you start to see these sort of interventions working really well. So you see this. Right. And what we see here, this is the probability of achieving elimination over 40 years. This is for different levels of treating visitors. If you do not reduce transmission, it's only if you're treating 100% of transmission that over time you will stochastically eliminate. If you have transmission reduction, you're much more likely to eliminate. So what this suggests is that you have to really stop elimination and have additional ways of reducing transmission on Zanzibar. So elimination is very difficult. And here we looked at probability of eliminating. These is saying no transmission reduction on Zanzibar, 50% and 90% transmission reduction. And the different lines show how much transmission reduction we have in mainland Tanzania. So what this is saying is that if you really want to eliminate malaria in Zanzibar, you need to reduce malaria in mainland Tanzania where malaria is coming from. So in many places that are close to elimination, the best way to achieve elimination is to help the source countries or the source areas which are sending you malaria cases. So, one example would be if South Africa were to target malaria in Mozambique, it'd probably be more likely for South Africa to get to elimination. I think it just, again, because I'm running out of time, I sort of will conclude. So again, in both these islands, it's really importation that's driving transmission, and we can reduce incidence through improving interventions, but really we'd need to get all these interventions together. And if we want to eliminate, we really need to target malaria on both mainland Tanzania and Zanzibar to get rid of malaria. And again, this is a relatively simple model. So we didn't consider seasonality here, either in transmission levels or in travel. We looked only at importation from Tanzania, not from other countries. And we didn't look at heterogeneity within the island. And there's probably foci transmission within the islands too. And we also didn't consider the relationship between infection and disease symptoms, right? So you can't, because with malaria, you can be infected without being infectious. And again, I want to thank all the people. Most of this work was done by Mimi Das, who's highlighted in bold. This was part of her PhD work. I thank our funders from the Gates Foundation, the Zanzibar Malaria Elimination Program, and also collaborators from Tulane. So I think that's it. I'm happy to take any questions.
Okay, thank you so much, Prof. Thank you so much for that presentation. So please, we have really learned a lot. Do you have anybody that have any question for Prof or any comment? Okay, one question, just one question. Okay, online participants, do you have anybody that have questions for Prof? You can just raise your hand. Anybody with question for Prof? Okay, so please, we take the first person now.
Thank you, Prof, for that wonderful session with us. Prof, I observed somewhere where you talked about the control of malaria, saying that the killing of the adult mosquito would be a better way of controlling than killing the larva. Please, can you expatiate on this? Because I thought it should have been the other way around.
Yeah, thank you for that question. That's a very good question. You can see it. Maybe if I'll stop sharing. I will share a different slide from another talk, which I think explains this better. I think you can see that now. So this is a schematic of the malaria life cycle. So this is when a mosquito bites an infectious mosquito bites a human. There's a probability B that leads to the infection taking place in the human. The parasite then infects the red blood cells. It makes the person sick. The person is infectious for, here we're saying if the recovery rate is gamma, and you saw this in the talks yesterday on compartmental model, like the SIR models, if that's the recovery, if gamma is the recovery rate, 1 over gamma is the duration of the infectious period. M is the ratio of mosquitoes, so the number of mosquitoes per human. A is how often a mosquito bites, so the number of mosquito bites a person gets per day is M times A. So M times A over gamma is essentially how many mosquitoes bite a person while the person is infectious. Then we have C here, which is the probability that the human transmits to mosquitoes. So we can see this then going into the mosquito. Mu is the mosquito mortality rate. Tau is how long it takes a mosquito to become infectious once it's infected. So e to the negative mu tau is the probability that a mosquito that is infected lives long enough to become infectious. And then again, A is the biting rate of the mosquito, and mu is the mortality rate of the mosquitoes. So A over mu are how many infectious bites a mosquito is expected to have over time. So if you multiply all of these together, you get the expected number of new infectious cases you get from one infected individual. So that's R naught, which is the mosquito density times A squared BCE to the negative mu tau over gamma mu. So if you kill larval mosquitoes, you see it here that you would just be reducing M. So if you have half as many mosquitoes, you'd have half as much R naught. If you kill adult mosquitoes, you have an impact here because you're reducing how many infectious bites they would have. But it has a huge impact in this exponential, where you're reducing the probability that a mosquito survives long enough to become infectious. And that's why when you kill adult mosquitoes, you're killing them in this time, because mosquitoes don't live very long. They usually live about 2 weeks or so. And it's about the same time that it takes a parasite to become infectious. So if you kill adult mosquitoes, then many infected mosquitoes will die before they're actually infectious. And if I go back to the other To the slide I was sharing, and you can see what George McDonald showed here. This is the probability, the daily survival probability of a mosquito. That's how many bites you expect to have. So if a mosquito has a 5% chance of dying per day, you think you can, according to whatever, these parameters, you have 200 infectious bites from each mosquito. If you reduce that by 5%, you get a tenfold decrease. If you reduce that by another 5%, you get a fivefold decrease. So you can see that this goes down very quickly. So again, because mosquitoes need to live long enough to become infectious, that's why killing adult mosquitoes has a much bigger impact.
Right, thank you so much, sir. I hope your question is answered, sir. So we have another question. All right, thank you so much, Professor Nako, for that beautiful presentation. And of course, you can know that most of the time, your papers are always papers we'll look out for. So while working on malaria,
His email.
so body gets quite exciting concepts to be on. You were saying something when you were presenting, and I really want you to speak more on that. The last model you were talking about, calibrating using prevalence data. Okay, now I don't know what's the best practice that you would suggest. Prevalence data, points data. Most of the time, for instance, the one we have, DHS is just collected, maybe once in 5 years. So you have that kind of data,
this guy is compatible with it.
model with that. So, what's the best practice? How should we about it? You suggest that you combine that with possibly
you get all the
correlations data as well. Maybe find it if it's possible if you have it. But if you don't have it, what do you suggest that we do? I think I'll also say so. With the with the equilibrium, equation for the infectious compartments and fit that. But then I don't know how reliable will that be. So just wanted to speak to the best practice around that. Which when you have prevalence data only, and then when you have maybe case counts only. And then maybe when you move to thank you, sir.
Yeah, thank you very much. There was someone else talking, so I'm not sure I heard everything. But yeah, generally the more data you have, the better. I think there's no way around that. And it also depends on the type of model you have. So this is a relatively simple model. There's not many parameters. So in this case, what we did was, as you said, we looked at the equilibrium prevalence of each of these. And we had prevalence from the 3 different places. So we had some data on where people, they sort of went around asking, they conducted a survey where they asked people, of the last 7 nights, where did you spend each of your nights? And malaria transmission usually happens at night, so it makes it easier. You don't need to know how much time you spend in different places, but really where are you spending the night? So from there, we know for each of the residents where these residents spend their nights. How much was it on their home island, how much was out in the other Zanzibari island, and how much was on the mainland. We also had some data from the mainland, so we could parameterize. From this, we could parameterize sort of how much time people were spending everywhere. And then we used the prevalence data to fit the transmission rate. So it's really these sort of these transmission rates beta that we fit from the prevalence data. So if you have prevalence and you have a compartmental model like this, you can fit the transmission rate. If you have incidence, data, which is always better. If, it's great if it's something like DHS data, but as you say, it's not collected very often. But in some cases, you can also use health facility data, which tells you how much transmission there is. That allows you to then fit more complicated models. It would allow you to fit models with seasonality, for example, or to fit models where you have interventions and how effective these interventions are. So really, the best practice depends very much on the kind of data you have and the kind of model you have. And it would be important to not, if you don't have a lot of data, it's better not to have a very complicated model, because you want to make sure you don't over-parameterize your model or overfit your model. So if you have little data, then it's better to have a simpler model. If you have a more complicated model, that's okay. If you fit the model from other data from other places, that can also sometimes work. So I hope that answers the question.
Yes, sir. Thank you so much, sir.
Okoya.
So, yes, so I'm still trying to, Prof, I'm still trying to clarify something. Please, can you go back to the place where we have the data at the table for that data? Okay, great. So now, prevalence is obtained here. Prevalence which is obtained for each location, member, Unguja, and mainland. And each of them is a points data. So now I want to believe that the equilibrium equation for the infectious compartment was fitted to each of these points separately for each location to obtain to estimate the parameter that you have mentioned there, which is the transmission rates. So I was looking at it as points that are just 1 point. So like I was thinking that what some people suggest is that maybe if you have this prevalence over age, that maybe you can then express it. But in this case, now I'm saying that you have a prevalence for each of the location, just a point. So please, can you speak more about this and then the practice around this? Maybe one can still go ahead and use this kind of thing to estimate such parameter, and then maybe to also now maybe simulate the cases as the case may be. Thank you, sir.
Yeah, thank you. So you're correct. It's just, this is only point data, right? So we just have the prevalence for the 2 islands, then we had prevalence for the mainland. If I move to the equations, we have, wait. So these beta here, these are the transmission rates for each of the 3 locations. We have the time that people spend in different places from the survey. So again, because it's really one, so it's three parameters that we're fitting. So it's the transmission rate for the 3 different areas, and we have sort of three data points. So this works. If we had 8 stratified data, with this model, we wouldn't really be able to use that data because we don't have age in the model. So we would have to take the average over the population. If you had a more complicated model, which included age, then we could use, for example, the age stratified data. So it's really, yeah, in this case, it's sort of, it's a relatively simple model. That's all the data we had, and that was enough. So that worked. We can still simulate, I mean, with this model, because it's such a simple model, it doesn't really distinguish between incidence and clinical disease. It's not the best model to try to simulate number of cases. I think it's good for simulating prevalence because that works. If you wanted to simulate clinical incidence, it would make more sense to use a different model, or a model that captures that distinction between incidence and disease, or disease and infection more appropriately. So I don't know if that answers your question.
Yeah. Okay. Yeah. Yes.
Thank you, Naku. Yeah, thank you, Naku, for that wonderful presentation. I hope you'll be able to send on the slide.
Yeah, sure. I'm happy to send the slides, and the paper is also published, but I'll send the slides to you.
So thank you. That pool has been a great break. And I pushed my postdoc in Switzerland. We had a great time together, and we are still working together. The last paper we published recently, was it 2 days ago? It was part of it, and I made some contribution. Thank you so much. And I want to also appreciate that I've been telling him for some time. He's a very busy guy, and he eventually gave me his word that he was going to come to give the talk. Although I was thinking I was going to come to Nigeria because we've been discussing about that, but eventually he could not make it. But I hope maybe the next show we are going to have, you will prepare yourself to come around. Am I saying your mind?
Yes.
Napu.
I'll do my best. And thank you also for the invitation. I'm sorry I couldn't make it this time, but I hope to do so another time.
Applause.
Yeah.
So have a wonderful day. Thank you.
Thank you very much. Yeah. Thank you. Bye-bye.
Thank you so much, Professor Napo. So, thank you so much. So, okay. So we're going to be moving on to the next session, which is going to be a parallel session. So, Professor Napo, we can.
Yeah.
Okay.
Thank you. Bye-bye.
All right, so we continue our parallel sessions this morning. So for machine learning, AI, and statistics, we're going to be using our room over there. While pure mathematics and applied mathematics are still going to be staying here. So please, you're in AI, statistics, machine learning, please let's move to our room. And then if you are in pure and applied mathematics, you can still stay here. So please, let's start that. So for the virtual participant, please join the room. So if you are in statistics, just join the room for statistics. Just click on the three dots, click on where you see breakout room. Join the room, statistics room. If you are in pure and applied math, you'll still be able to.